This is the 5th video on simple feedback design and gives some tutorial questions. So we're going to assume that students have looked at the first few videos on heuristic design. And the purpose of this video is to provide some tutorial questions so students can test their own understanding. What we want you to do is read the questions, then pause the video while you attempt to answer the questions, and then look at the solutions afterwards to see the view that we're giving. Now some background. We're going to assume a simple feedback loop with a PI compensator, a bit like this. Now for heuristic guidance, which is designed ideally for first order systems, and with t the desired closed loop time constant, we've said that you can use a compensator a bit like this. You'll see m of s is 1 over g of 0, that's the steady state gain of the system, times 1 plus 1 over s capital T. And obviously you can write that as a proportional term plus an integral term. And you're reminded that for higher order systems this choice of integral might be slightly large and you might want to reduce it a little bit. On with the questions then. So question 1. A domestic heating system with input in kilowatts and an output of temperature difference compared to the external temperature can be modelled by a transfer function g of s, and you'll see g of s is given here, and the time units are hours. The maximum power available is 50 kilowatts, and the maximum expected temperature difference between what you want inside and the outside is 30 degrees. Now we're going to propose a compensator, a PI compensator m equals 4 plus 6 over s. And what we want you to do is to discuss the efficacy of this compensator and, if appropriate, suggest improvements. And please do use Matlab to check your working. So now's the time to pause, and I will go on and look at some possible answers. So first of all, let's see what we get in terms of the closed loop. So we can write GC equals GM over 1 plus GM is going to give me the closed loop transfer function. And I've got M, if I rearrange this into a neater form, is 4S plus 6 over S. So if I put those two together, I get GC equals 0.4 into 4S plus 6, all divided by 0.4 into 4s plus 6 plus s plus 0.5. And this, if I multiply it all out, gives me 1.6s plus 2.4. I'm less concerned about the numerator for what we're doing here. And then s squared plus 2.1s plus 2.4. Now the key thing is to look at this closed loop pole polynomial and say, what does this look like? Well, I can rewrite this as s plus 1.05 squared plus 1.14 squared. So what does that tell me? One, it tells me that the time constant is approximately 1. You can see that because I've got an s plus 1.05. But it also tells me that I'm under damped. You can see that because we've got a frequency of oscillation here of 1.14. Now what other things can we look at? Well, we can look at, for example, the input activity. So let's do that. Input activity. And you'll notice that u of 0 equals kp times e of 0, which in this particular case is 4 times e of 0. However, you can also find the steady state. So u steady state equals g of 0 times r, and in this particular case g of 0 is 0.8, so you get 0.8 times r. Now what's significant here? The steady state multiplying factor is 0.8, the transient multiplying factor is 4. So in other words, the transient u of t is 5 times bigger than the steady state. And that's something that you might be worried about. Now if you look back at our criteria, we said U max equals 50, R max equals 30. So let's put these two values into this formula here, and what you get is U of 0 equals 4 times 30, which is 120, which is much, much bigger than 50. So for this particular choice of compensator, you're going to get underdamped behavior, which you might not be too impressed with, but also the initial value of the input cannot be implemented for large set point changes. Okay, so as soon as the set point change gets close to 30, you can see immediately the input the compensator is asking for just cannot be delivered. Alright then, let's have a look at the heuristic design and see what this tells us. So if we go with the heuristic design, we have 1 over g of 0 into 1 plus 1 over st. We have to choose a sensible time constant, which in this particular case, because you have that there, a sensible time constant might be t equals 2. So in other words, the heuristic design is going to give m equals, now 1 over g0 is going to be 1.25, then I'm going to get 1 plus 1 over 2s. And I can simplify this a little bit if I want to. Simplify this, then you'll see I get 1.25 plus 0.625, oh I forgot the s there, 1.25s plus 0.625 over s. So this is my heuristic compensator. So what happens if I put this into the system and find out what I get? So gc equals gm over 1 plus gm. So what I'm going to get is 0.4 into 1.25s plus 0.625, all divided by 0.4 into 1.25s plus 0.625 plus s plus 0.5 times s. Now if I multiply this all out, you'll see that on top I have 0.5s plus 0.25, and underneath, multiplying this all out, it's going to be a bit of a mess, but you'll see I get s squared plus s plus 0.25, and if I just put under this so you can see, this is actually s plus 0.5 squared, and so looking at the common factors, this reduces to 0.5 over s plus 0.5. So a much nicer looking form with the time constant that you would like. Now, finally, a question that might be interested to ask is what's the maximum kp? So what you'll remember is we said that the maximum u was 50. So u max equals 50 equals kp times R max, which is going to be kp times 30, tells you that logically kp should be less than or equal to 50 over 30 if you want to avoid saturation. And you'll notice here that the kp we've chosen is 1.25, so we can increase the kp slightly if we want a faster response than something matching open loop dynamics. So what I'm going to do now is move to Matlab and see whether we can reinforce these computations we've done on paper. So first of all, let's enter our system, calculate the closed loop transfer functions, and look at the poles. So there's the standard commands, and what do you see for the pole positions? Minus 1.05, plus or minus 1.14i. So as we calculated, and you're expecting some form of oscillation. Now we'll do the plot in a minute, but next let's enter the heuristic compensator, and I've called that M2. You'll see that's what we said. And I've also entered a compensator here, M3, which is the one which gives you the maximum kp possible. So all I've done is scaled up those two coefficients in M2 in order to make the kp 1.67. So that should speed up the response a little bit. Then we calculate all the corresponding closed loop transfer functions. There you go. And then finally, let's look at the poles for these two. So you'll see a pole at minus 0.5 as expected with heuristic design, and with a slightly bigger KP, you'll see we've speeded up the response a little bit as expected. So now let's look at some figures and see, does this do what we expect? So first then, this one looks at the original compensator and the heuristic compensator. The original compensator, can you see that the proposed input goes up to 120? Very, very large, much, much bigger than the steady state. And remember, we actually had a limit of 50, so this couldn't be delivered in practice. With the heuristic, we have the input, you can't see it very well here, it doesn't change, it's like a step, it's just constant all the way along. If we look at the two outputs, with the original controller, very fast response, slight overshoot, it was underdamped, but settles quite quickly. With the heuristic, not nearly so fast, settles a bit more slowly. But of course, you've got the faster response by having an input here, which was unrealistic. Now, what about if we push the PI just a little bit harder, as we said, by going to the limit? So there, we've done the response. We'll just go to the window. So this one is looking at M2 and M3. So the heuristic is now this blue one. And you'll see by increasing KP up to 1.67 instead of 1.25, we've got a slightly faster rise time, slightly faster settling time, but we've paid for it with a slightly bigger input during transients. And hopefully, therefore, you can begin to see how this heuristic design is helpful. It's given you a start point which has an input activity which is fairly flat. If you want to get a faster response, you can see it is possible to push it slightly, but you pay for it with a more active input. Question 2. So a tank system has a transfer function g of s between input flow and output depth. Derive the closed loop transference between the target and the output, and hence comment on the expected closed loop performance. And you'll see the values are given there. So now's the time to pause, and I'll continue and go through a solution. Alright, first thing to do then is look at what we've been given. So I'm going to calculate GC equals GM over 1 plus GM, and in this particular case I get 10s plus 30 divided by 10s plus 30 plus s squared plus s. Now, I want to look at this closed loop pole polynomial, and if you expand this out, you'll see this is given as s plus 6, s plus 5. So it's very fast compared to open loop. You'll see the open loop has got a pole position here -1, and now we've got pole positions -6 and -5. So we're expecting a very fast response. Now let's look and see how we achieve that. If I look at u of 0, you'll see it's going to be 2 times e of 0. Whereas if I look at u steady state, it's going to be 0.2 times r, which essentially is the same as e of 0. So what do we notice? The initial u of t is 10 times bigger than steady state. So what we've got here is quite an aggressive control law. So when we move to Matlab, that's what we'll be expecting to see. Now what if we look at the heuristic design? What would the heuristic design do for us? Well, we've got g of 0 equals 5, and we've got t equals 1. So that's going to give us m equals 0.2 plus 0.2 over s. And if I substitute that in and do gm over 1 plus gm, I'm not going to write all the algebra for you, because you'll be able to do that yourself, and you'll see you end up with 1 over s plus 1. So it matches the open loop time constant, which is what you expect, and it gives you a closed loop gain of 1. So let's have a look at Matlab and see if, again, what we've derived happens when we try it in practice. So here we go. Go down and look at example 2. So there's the G and there's the K. Can enter them. Here's our heuristic design. We've called it K2. Entered there. Here's all the closed loop transferences, standard statements, which you'll be familiar with by now. And let's look at the poles. So with the proposed compensator, there you see poles -6, -5. And with the heuristic compensator, pole at -1. So next, let's do the plots and see what we get. So there you go, and you'll see with the proposed compensator, the input, the red curve, goes all the way up to 60 and comes down and settles down here at 6. Whereas, that's because I've set this target as 30, that's why it's gone up to 60. Whereas the input with the heuristic, you'll see, has gone straight to the steady state value and stayed at steady state. A consequence of having this aggressive controller is you've got a very fast output response. You remember, well, you'll see there's a slight overshoot here that might or might not be expected. With the heuristic, much slower and smoother response. Now, you might want to explore a bit and say, oh, well, what about trying to get a compensator somewhere in between? So I'm going to use this file, which I've written overlay many, which allows you quickly to try different compensators and see what happens. So you'll see what I've done here. You put in your system G, and then you put in your different compensators, K, K2, and I'm going to add a third one here, and you'll see it's 1, 1 over 1, 0. It's roughly halfway between the other two compensators in terms of the gains. So let's run that and see what happens. So there we go. You'll see I can very easily get a compromise between very fast, the blue, quite slow, the heuristic, and you see the red is this compromise compensator. And if you look at the inputs, you'll see the heuristic steady the whole way through. The red starts at 1, so it's 5 times more aggressive, and the blue 10 times more aggressive. So I can easily explore with Matlab what happens as I change compensation just by sticking all these K's in here and tweaking things a bit, and therefore fine-tuning starting from a controller, which is reasonable. Example 3. So again, you'll see it's the same sort of question. We're given a G, we're given a compensator, and we're asked to investigate and say, what do we think? So let's write this down. GM over 1 plus GM, in this particular case, can be written as, and perhaps I should rewrite this M here just so you can see what I'm doing. I can write that as a third into S plus 2 over S. I'm going to write it like that. It makes life a bit easier. So what I've now got is GM over 1 plus GM is going to be S plus 2 over S plus 2 plus S squared plus S, which can be written as S plus 2 over S squared plus 2S plus 2, and you'll probably spot straight away that this can be written as S plus 1 squared plus 1 squared, and therefore it's under-damped. So you'll expect a little bit of oscillation, but not a lot, because it's not a lot under-damped. Now again, we'll try and understand why is it under-damped, what's gone wrong with this compensator. So let's explore. First of all, U of 0 is going to be a third times E of 0, because you can see the KP is a third. U steady state is going to be a third times R, and so what you notice is these two are essentially the same. So it's telling us that KP matches the heuristic. Okay, heuristic design. What about KI? Well, in this particular case, what have we got? We've got that KI equals 2 over 3s. But if you look at the heuristic design and you notice that the desired time constant there is 1, then the heuristic design would have ki equals 1 over 3s. And you'll see these two are not the same. In other words, the integral is too large. And so this oscillation, this underdamping, has happened because you've made the integral bigger than it needs to be. And if you want to reduce it, you could try the heuristic, which would be a third into 1 plus 1 over s. And you see it's not a lot different, but the key thing is having these insights allows you to quickly identify where the problem might lie. So let's go to Matlab and have a look at this one. Okay, so here's my systems. So first of all, I'll enter in the controller I've been given, and there you can see the poles come out at -1 plus or minus 1 or 1i or j. I can do a figure for this and see what's happened, and there you can see the output response overshoots slightly the input response. The input starts at the right place but goes a bit too big, and that sort of gives you an indication I'm integrating up too fast based on this error, and that's why the input has gradually gone too large and why I've ended up with this overshoot. So the plots also give you an indication of what might be wrong with this compensator. Now I can use this overlay many file and put in the heuristic, and what do you notice? The heuristic is the green. I've reduced the integral slightly. I've got the same settling time, but it's just a bit slower to get to the target, and it doesn't overshoot. But the advantage of the heuristic is the input flat, not overly aggressive, doesn't go too high, whereas the original compensator with the high integral, you can see, oscillated a bit and went much, much larger. Now if I want to, I can play around with other compensators, put in this overlay many, and if I just go along here so you can see, what have I done? I've tried here putting in an integral which is somewhere between the two, or rather just, you see I've put 1 over 2, 0. So I've just increased the gain very, very slightly. And what do you see? By increasing the gain very slightly, I can get this red plot which lies between the green and the blue, but the initial input is much more aggressive but does change smoothly. So you've got a mechanism here where you can do some fine tuning, where you can say what happens if I change kp a bit or change ki a bit, and how do I get the best compromise between the different things I'm looking for. So conclusions. We've given some tutorial questions and work solutions on heuristic PI design, but we should emphasize that heuristic is not an ideal solution. It's an indicator of likely values, and hence a good place to judge whether the design you're using is approximately correct. There are, of course, more formal design methods which will be discussed elsewhere.